Hey everyone, welcome back to another episode of Everything Embedded. This is going to be a continuation of the power supply series where I've actually built up the boards that we designed previously, and we're going to run some measurements to see how well they perform and do a little bit of tuning and tweaking on them to optimize their performance. The first measurement we're going to run is an efficiency measurement, and this is to get a baseline for any changes that we make to see how those changes affect the efficiency, as well as just compare where they're at now. To make this measurement, I have a DC electronic load, so this will allow us to draw a set amount of current, and I've got a DC power supply here that we can measure how much power we're putting into the supply, and then the ratio of those tells us how efficient they are. So here's the test setup for making this measurement. So what I've got is the power supply right here and our DC load here, and I've got them connected through banana plugs to the board. I'm using the external sense functionality on both of these. So this one has sense ports right here. Here's the sense plus, and then the sense minus is underneath it. And this guy has sense ports over here to sense the voltage closer to the board. This will take any voltage drop from the cables out of account so that we're measuring this right at the board at the same point on each device. What I'm going to do is step through different output load currents on the DC load, starting from 0 amps up to the 6 amps that these regulators are rated for, and then we'll measure how much input current is being consumed, and from that we can calculate our efficiency. One thing to keep in mind is that my supply here only goes up to 1 amp. To get to our full 6 amp output load current, I'm going to have to use a little higher voltage than the 24 volt nominal that these are designed for, so I think we're going to run them off a 30 volt input. So for this regulator, starting out here at 0 volts, we have 5.3 volts output, and we have 6 milliamps of input current. So this one is not super efficient at light loads. So for my test procedure here, I'm walking through in 100 milliamp increments up to 1 amp, and then once we hit 1 amp, I'm jumping in 500 milliamp increments. I'm noting down the input and output voltage as well as the input and output current into a spreadsheet, and from there we will calculate all of our efficiency curves for each of the regulators. To go above 5 amps for the output current, I increase the input supply voltage to 35 volts. This won't really be valid for looking at a curve of the efficiency, but it at least gives us a number we can use to compare the supplies off of. I was able to get up to 5.9 amps output on this supply at 35 volts before I current limited my supply. I've gone ahead and switched over to the 500 kilohertz LMQ61460 supply, and we're going to run through the exact same set of measurements. Last here, I've switched over to the 2.2 megahertz switching frequency regulator, and we will run through the same set of efficiency measurements. At this point, for the 2.2 megahertz regulator, I start running into an issue. At higher switching frequencies, the regulator is less efficient, and with the design I did, I don't have really good heat sinking on it, so it starts to thermal throttle. Above about 5.5 amps, we can see that the output voltage does not remain stable as the regulator is working to reduce the heat generated and protect itself. So now that we've completed these measurements, I've gone ahead and graphed them in Excel so that we can compare between the regulators. And so on top here, we have the 500 kilohertz design. In green, we have the 2.2 megahertz design, and in orange is the LM25088, which is the discrete design. And the first thing that's very apparent is down here in the low current region, the LMQ61460 has much lower quiescent current draw. So this is basically the current required to just run the regulator. And so for light load applications, we can see that this is drawing way less current, whereas this takes quite a bit of current just to run the regulator. It's not being lost in the switching path. It's just the current required to operate the internal circuitry. The other thing that's apparent is that there's a big difference between the switching current, there's a big difference between the efficiency as we increase the frequency. So out here at 4 amps, there's about an 8% difference between the 500 kilohertz and the 2.2 megahertz switching frequency. We can also see that the LMQ61460 at a similar switching frequency is quite a bit more efficient than our discrete regulator design. It's important to keep in mind for looking at efficiency numbers that a small change in efficiency can be actually a pretty big difference in power loss. So out here at 5 amps, for example, the 2.2 megahertz regulator is exhibiting over 4 watts of power loss here. The discrete regulator is at 3.3, and this top regulator here, 2.1 watts. Now that's almost double the power losses, so even a small change in efficiency here means we have almost twice as much heat that we have to get out of the circuit, and that can make a big deal, particularly in devices that are enclosed or don't have a lot of cooling. That heat can cause big problems. Before I perform any more tests on these, I want to make a small design optimization. One thing that can be an issue for some converters is ringing on the switching node. This can lead to really bad EMI problems, and in some cases even damage components such as the switching MOSFETs. The best way to reduce ringing is during layout by ensuring that the switch node has really low parasitic inductance. However, I want to measure to see if there's any ringing on these regulators. So what we're going to do is take a measurement of the switch node with an oscilloscope probe here. If we find any ringing, I have provisions built into all these boards to tweak the gate rise time to reduce or eliminate the ringing through some resistor value changes. Since increasing the rise time can have a negative impact on the efficiency of the supply, after the design has been changed, I will rerun the efficiency measurements so that we can compare this change. Since the ringing can be very high frequency, often well over 100 megahertz, it's important to use good measurement techniques with the oscilloscope. So to make the measurement, I've attached the spring tip for ground on the oscilloscope probe so that we don't have the large loop inductance of the ground clip, which is not good for high frequency measurements. I'm going to make these measurements with each supply running at 4 amps of load current, which is where I would expect to run a supply with this rating most of the time. To make it easier to access the board and make the measurements, I've removed all of the sense lines and turned off the sense settings on my supply and load. So here I'm measuring the switch node ringing for the LM25088 converter. We can see here in the oscilloscope capture that the ringing is really bad. It's peaking at over 50 volts. So I will add a resistor to the gate drive to increase the rise time, which will help reduce the ringing. So here is the same measurement with a 22 ohm resistor on the gate driver. We can see that we've reduced it quite a bit, but I would still like to reduce it more, so I'm going to add some more resistance. Here's the ringing measurement with a 33 ohm resistor on the gate drive. There's still some ringing here, which could be dealt with a snubber, but this is more in the realm of what I would consider acceptable. Here is a scope capture from the LMQ61460. This is the 500 kilohertz board, and we can see that without any modifications, this waveform already looks really good. There's a couple little ripples on it that I want to clean up, and so I did add a R boot resistor, which cleaned it up so that it looks like this. This looks really good, and by slowing down the rise time a little bit, this will also help roll off the harmonics of the switching frequency in the overall emission spectrum. So after we made the gate drive adjustments, I went ahead and reran the same efficiency tests between the LMQ that's at 500 kilohertz and the discrete LM25088. And it's interesting to see that since we didn't make a whole lot of change to the LMQ regulator, between the gold and yellow lines up here, we see almost no change. However, for the LM25088, we get anywhere between 2 and 3% efficiency reduction because we had to slow the rise time down so much to reduce that ringing, and we didn't even fully eliminate the ringing for this one. So this is where we can see what seemed like not a huge difference before. Once we actually take some of the EMI issues into consideration, our efficiency numbers actually look much better for the LMQ regulator instead of the LM25088. So that's going to be it for this episode. In the next episodes, we're going to take a look at some near-field probe EMI measurements to compare these two regulators, and we'll also take a look at the transient and output ripple performance of these regulators as well. Thanks for watching. If you have any questions, please be sure to leave them down in the comments.